Good afternoon again, students. We are going to continue from where we ended on the sixth presentation, and we'll consider this as presentation 6B. And it belongs to the last parts of this module, parts C and D. And at the moment, we are looking at a number of issues that are connected with this enhanced diagram of what we are dealing with. We have the colored parts, and these colored parts are which concern the use of quantitative genetics, and then, of course, connected to the selection predictors, and then the application of the selection index. The ones then that are on the bottom progressing to the left are the parts that will be concluding this module. And as we progressed before, these are the aspects that we already talked about. I want to remind you that this part that is colored as given belongs to the area of the quantitative genetics. And this quantitative genetics part of our interest belongs to the quantitative genetic theory. Quantitative genetic theory provides a basis for designing, evaluating, and improving plant breeding programs. That's why it's very essential for us to understand some of the issues connected with the genetic theory relevant to plant breeding. So the first part of the issue is about the QTLs. And we talked about the QTLs before, looked at the two characteristics. And we then came to the second concept, which is heritability. And the heritability is of interest when you have certain loci with alleles that are trait determinants or trait determining. And so we saw what the professor did last time. And from here, we want to continue with the issue that goes a little beyond heritability, but for the moment, hopefully in this particular lesson, we will look at heritability a little further. And this caution, I've already circulated it to you, that please do not jump the sequences. This is why I've given time to ensure that everybody is at the same level so that we move together. The aspect, we consider the QTL. We know what QTL is. We have the issue of heritability, which we cannot deal with until we have introduced in the further issue of the phenotypic variance. Remember in the introduction, I already indicated the importance of variance. And so variance, we talked about additive variance, but we'll see that we cannot swim right into the idea of additive variance unless we begin with the bigger picture of the phenotypic variance. Because remember, the variation we see, we observe by our eyes, is phenotypic. And in this regard, when we are looking at a particular character value, a particular trait value, we may see that it may have a range of values, variation, which is on the vertical scale, the frequency. And so when we have enough or a large range of the total phenotypic variance, we can expect that variance to be bell-shaped curve distributed. And so here, coming back to here, we have three variances we are going to look at. The total ones are three total types: the total phenotypic variance, the total genetic variance, and what you may want to call the total environmental variance, although we don't have to use the word total. So we can decompose the total phenotypic variance, the V sub P. We can decompose it in this way, that it is the sum of the total genetic variance plus the sum of the environmental variance. And basically, that's how the total phenotypic variance is defined. Remember the word total to precede the variance so that we are moving with the same understanding. Then we can further decompose the total genetic variance as follows. We can decompose it as having additive genetic variance, which is of very paramount or primary interest. And also decompose it into the component that is V sub D, the dominant genetic variance. And further decompose it to V sub I, the epistatic or interactive genetic variance. That's when we look at the blue on the right here. We can see that we have a decomposed total, the total genetic variance as seen into the VA, VD plus VI. Again, that total genetic variance, as one can see here, is actually normally distributed. When it is total, it is large. With these decomposed variances, then we can go to talk about heritability by two categories. When the first category of heritability is one that is called broad sense. And that broad sense is simply the total genetic variance over the total phenotypic variance. It is called broad sense heritability. It's not very useful in plant breeding, except under exceptional situations that it can be alluded to. So when we are looking at what we're calling the genetic effects, consider that the genetic effects, the G, is actually the total genetic variance. And we have seen that if we ignore the interactions, it is where it is the sum of the additive plus dominance. In this regard, A, as said before, is the additive effect. And this additive effect is again the sum of the breeding values. And we'll shortly come to the idea of breeding values later or shortly. And then the D is the dominance deviations. So the dominance deviations are the ones which refer to the deviation of the genotypic values from the sum of the average effects of those genotypes, which can result due to the interaction between alleles at the same locus. Alleles at the same locus. And when we talk about alleles at the same locus, you can consider the lengths of specific parts, or the height, or the weights of some objects, like even birds. Birds have been shown to have genetic variation between species or between populations within species or between the sexes, and depending on the age and condition of birds. So we shall be using the bird as an example to illustrate how heritability is obtained from the data taken. Such data have provided the estimates of heritability. I'm recording, I'll call you. Such data have provided estimates of heritability that are important in terms of our understanding of how individual characteristics are transferred between generations. Remember, again, I want to emphasize here that the estimates of heritability are important to provide our understanding of how individual characteristics are transferred between generations. So we come to the other category of heritability. We talked about broad sense heritability, where we've seen that it really is about total proportions, total genetic variance over the total phenotypic variance. In contrast here, the narrow sense heritability, note, is the VA or additive over, or a proportion over, the phenotypic variance. The H with the power 2 is not square, it's just is a symbol that represents heritability as an abbreviation. So again, continuously you see this normal distribution because variances are normally distributed when they are large. And if they are representing the allelic variation, then they are normally distributed. And this normal distribution is extremely, extremely important for us to put in mind every time we're looking at a character value versus the frequency of that variation. I hope you understand this, my students. I hope you do. So as we have the narrow heritability here, we know that it is representing or reflecting the changes in allele dosage or allelic substitutions. So these additive genetic effects are also referred to as the breeding value. As the breeding value. I emphasize the word breeding value because these additive genetic effects as breeding value are the ones that are predictably transmitted to progeny, predictably transmitted to progeny. So the deviations from the additive effects are significant for many traits. And as we said before, they can be partitioned into either dominance effects that reflect the interactions between different alleles at the same locus, or epistatic effects resulting from the interactions among different loci. And we'll come to the formula a little later, which you must really remember because it brings in a number of things that we will be talking about. And as said before, we should not be listening to this presentation unless you have listened to the one by Professor on heritability that I sent in the lesson 6A. Now, what happens then when we want to look at another way of a narrow sense heritability? We see that it's a slope. It is a slope that results from regressing offspring value on mid-parent value. And so we will see that the slope is really a straight line, a slope. When we regress, it can be represented in the regression equation by the value b, the slope. So we can do that on mid-offspring regression, and we can estimate the heritability estimate. We can also regress a parent offspring regression, and we can see the value of the heritability getting to 50%, half sibs getting to 1/4%, first cousins getting to 1/8. As the groups become less related, the precision of the narrow sense heritability is equally reduced. Remember, heritability is simply an estimate. It can be estimated because it predicts what may be transmitted, what may be transmitted. And so when we graph and we can see, for example, the alleles at a single locus, like short to tall, if they have this kind of distribution, like we can see in A here, it's approximately 0. In B, if it is regressed and it's looking like that somehow from short to tall, and it has the semblance of a line, we can say it is approximately 0.5. And if it assumes a more straightish line, we can say heritability estimate of what is transmitted is approximately 1. But if, for example, we are looking at students and their parents, then we are looking at the mid-parent height of the the parents, for example, and then we look at the mid offspring height. We can determine a slope that you can see looks like B, for example. And one can see that it's not 1, it's approximately 0.084. Of course, we cannot look at regressing the heritability to estimate it on the teacher or lecturer height or effectiveness and the students. It just wouldn't make sense. It would be spurious. In fact, it would be literally 0. It would look like the A. Now, we need to recognize, as we end up in this session, so that it's a short one before I begin another one, that there are certain characteristics that must be noted about heritability. They are not constant. For example, estimates of heritability for the first lactation milk yield in dairy cattle nearly doubled from approximately 25 in 1970s to roughly 40% in recent times. So they are not constant. So you cannot use what happened in 1970s as heritability estimates of milk at first lactation of the old data. Also, allelic frequencies. If we look at the genetic variance, the total VG, with those components, they can change if, in fact, allelic frequencies change. And these allelic frequencies can change due to selection or inbreeding. For example, at F2 or F3 or F4, they can change as new variants come into the population by migration or mutation or even selection, or if existing variants only contribute to genetic variants following a change, and that change can come from selection, a change in genetic background, or a change in the environment. Then we also can expect heritability to change over time when the variance in genetic values have also changed for some reason or another. Environment factors can also change when the environment, due to environment factors, change. So, can change. The other aspect is that trait influenced by age, because remember we have age alleles, age determining alleles. And if we have age determining alleles that have been switched on, for example, as we age, then they change the trait. Get a guy who's working, a young lady who is vibrant, walking straight, having non-wrinkled face and smiling and energetic. And then you get one who is aging, and some of the age determining the alleles that are age determining, they change the trait, then you can begin to see that if we measure a same trait over an individual's lifetime, they may have different genetic and environmental effects influencing it, such that the variances become a function of age. We don't know how human breeder would have estimated or made a heritability estimate of Isaac based on the old age of Sarah and old age of Abraham. But probably the heritability estimate would have been God controlled because that was God designed birth at a later stage. So why is knowing heritability important? And the answer is because it allows us to predict parental traits response in the expected offspring to selection. Why? Please don't leave this issue of heritability estimate without seeing this primary importance. And we'll now see how we can take further this issue of heritability to the breeder's favorite question. But for now, I think we will have to stop at this point. And I would ask that you study a little more about heritability if you have not understood it, but these are just the basics of it. Thank you for listening, and let us look for the next lesson 7. Thank you.